Hi there, and welcome to the last part of On the Measure of Intelligence by François Chollet. This last part concerns the ARC challenge that Chollet has proposed, or the ARC dataset, which stands for the Abstraction and Reasoning Corpus. And we're just quickly going over the dataset, look how it's built, and discuss what kind of solutions might be relevant right here. So if you haven't seen the last videos in this series, this is the last one of a series. You might not exactly know what's going on, but I think you can keep up pretty well because this part is fairly independent of the other parts, and it's just cool to think about even if you haven't seen the other ones. I encourage you to go see the other ones, but it's not necessary. Okay, let's jump in. So the ARC is a challenge, currently running a Kaggle challenge. But in essence, it is a dataset. And let me just jump into one of the tasks of the dataset. So in this dataset, you always have the task in the following form. So you always have multiple input examples like this, or say these are called the training examples, and then you have a test example. In this case, you have 3 training examples, 1 test example. So an entire, if you think of this in a machine learning way, this entire thing here is your X, and this thing here is your Y, okay? So the label is going to be the output of the last example that you don't know that. Now of course, in the training data set you do, but in the test you don't. So each one of these, as I said, is demonstrated. These are the demonstration examples, and then you're supposed to sort of learn the regularity out of the demonstration examples, and then on this test example you are supposed to apply this regularity that you learned. So in here, a human can fairly accurately see that there are these black squares in each image, and that in the training samples the output will always sort of exactly match into the place of these black squares. As you can see, this is like a high rectangle. It goes here, it has the same amount of tiles and so on. And you can also see that whatever colors are in here sort of are the continuation of a symmetric pattern. So here, this is exactly the same as up here, but flipped or turned by 180 degrees. So there is a notion of symmetry right here. So technically one could compute this. One would say, oh, that's probably going to be the 3 rows and this bunch of things, and it's probably going to be the same as this one down here, but just flipped on its head. So as a human, you get this even without a description. You realize like, oh, this is like a regular pattern, it's symmetric, there's a hole in it, and apparently the thing here always fills the hole. I can see that, 3 examples are enough for me to confirm that that's what's going on, and I see the hole here, so I'm going to do the same thing. So you can already see how these things are constructed. This is not the only task, by the way. This is just one task, okay? There are 1,000 tasks in this data set of this sort of nature. Now, they're not always 3 demonstration examples. I believe there can be more or less. But what's always the case is each of these training examples consist of these demonstration examples and this test example. Each of the demonstration examples consists of an input grid and an output grid. The input grid and output grid, they can be anywhere from 1 by 1 to 30 by 30. Okay, anywhere in between that. And the colors here, I believe there are 9 different colors that are just encoded by 9 different numbers. But there are 9 different colors that these things can have. You can see black, blue, orange, red, dark blue, and so on. And the output grid exactly the same. Now, in this test example, you can only see the input grid. You cannot see the output grid, and that means you don't even know how large it should be. You can see right here, they're not all the same size, the output grids. In fact, not even the input grids have to be always the same size, but you have to now come up with an output grid you have to first decide how big it is, and we've determined, since the whole has 3 rows, we're probably going to make 3 rows, and it has like 7 columns, we're probably going to make 7 columns, and that's the sort of thing you have to do. And then not only do you have to decide how big it is, you now have to decide in each cell what color you put in. And only if this thing exactly matches the test label, you get a point. Otherwise, you get no point. Okay. So in the training task, there are, I believe, 400 of these tasks, and then there are 400 more as test split, but these are still public. And then there are 200 that are secret, that are, I guess, part of this Kaggle challenge. Yes, the training set features 400 tasks, while the evaluation set features 600 tasks. The evaluation set is further split into a public evaluation set of 400 tasks and a private evaluation set of 200 tasks. All tasks are unique, and the set of tasks and the set of training tasks are disjoint. Of test tasks and training tasks. The task data is available at this, as you can see right here. So I really hope that Chollet will keep these 200 tasks as a secret, even after the Kaggle challenge, because it's going to be fun for people that might want to get into this later. So here are the goals of this data set. They want to stay close to these psychometric intelligence tests. They say in particular it should be solvable by humans without any specific practice or training, and probably also without any language instructions. So you just be able to set a human in front of it, and the human should be able to solve it. Or a large portion of humans should be able to solve it, right? Ideally, this test would also differentiate humans from each other, but at this point, we want to simply assess machines. So they say focus on measuring developer-aware generalization rather than task-specific skill by only featuring novel tasks in the evaluation set. And the novel tasks are unknown to the developer of a test taker. So if I develop a system, I don't know what are these 200 tasks that Chollet keeps hidden. I simply submit my code, and I'll figure out if my code does well on them. So they say they want to feature highly abstract tasks, must be understood by a test taker using very few examples. And that's what you saw. You don't have a big training example to learn that this task is about symmetry and hole filling. You only have 3. And from 3, you need to recognize what's going on and produce the output of the test sample, right? Qualitative control for experience by only providing a fixed amount of training data for each task. That's what we saw. And only featuring tasks that do not lend themselves well to artificially generating new data. So it's not like ImageNet, where you can go on the internet and find a whole bunch of images, or some NLP tasks where people pre-train on all of Wikipedia and all of the books in the world because they want to understand language better. These tasks are supposed to be such that it makes no sense for you to go out and try to find more data or find similar data or pre-train your model on something. And then lastly, and this refers to the last few chapters we looked at, explicitly describe the complete set of priors that it assumes and enable a fair general intelligence comparison between human and machines by only requiring priors to those close to innate human prior knowledge. So that means that whatever humans have as a prior built into them by, let's say, evolution, or that most humans have picked up through life, those are the things that you have to explicitly point out. So, and you require that. And you have to point them out, explicitly describe them such that I, as a developer of a system, can build them into my system, such that it's a fair comparison. In the last chapters, we looked at the fact that a fair intelligence comparison is only fair if 2 systems that are compared to each other have the same amount of experience. And here we control that by only providing a fixed amount of training data, and also have the same prior knowledge. And here we simply do that by listing the human priors that are required for the tasks that we think that humans have, and then we enable the developers to explicitly build those into machines. So I would maybe build a little calculator module into my AI that solves this task. Okay, so they say each task consists of a small number of demonstration examples, 3.3 on average, and a small number of test examples, generally 1, although it might be 2 or 3 in rare cases. Each example consists of an input grid and an output grid. Each grid is a literal grid of symbols. Each symbol is visualized by a color. There are 10 unique symbols. A grid can be any height or width between 1 by 1 and 30 by 30, so it doesn't even need to be square, right? And as I said, you need to provide your own output grid as an AI taking this test. So here are the priors that this test assumes, and we're going to look at some examples that make it explicit, like some tasks in the training set where you can see these priors in action. So there is an object-ness prior where the task assumes that the AI, or the task tests that the AI understands something about objects. So these are tasks that you can only reasonably solve if you know something about objects, like a human would recognize, or would recognize that these things might represent different objects, right? Now that's mainly, I think, also due to the black background helps, but you would even recognize this with another background. Or here, the different colors indicate that those are two different things, even though those two pixels here touch and are different from black, you would recognize that those are two different things because they have different color. But you would generally recognize one of these things as an individual object if you're not given anything. Here you see, for example, a denoising task. As a human, you can pretty quickly see what the task is about, right? There appear to be these green things. They're all rectangles. And there appear to be these blue things. And on the right side, there are no more blue things. But now it's not always that when there was a blue thing, there is now a green thing. Only here, where it was sort of inside a green thing, is now a green pixel. Whenever there was a blue pixel outside in this black area, then there is now black. So this is sort of like the blue things were noise and you're able to remove it. So this already tests a lot of assumptions, a lot of these priors, a lot of understanding of the world. So there are objects, right? Objects, the human understands that objects are square in this case, or rectangles. The human understands that that we need to remove the blue things going over. And the human understands that somehow this inside relation, right? If something is inside or outside of one of these rectangles, and that determines whether we have to turn the pixel green or black. And you can, think about how you would train a machine to do something like this. It's not easy, especially if you don't know that this task is coming. Imagine, for all of these things, you don't know that the task is coming. This is just one of 400 tasks that you know of. There are 600 tasks that you don't know of that are similar, but also in a way completely different. Here's another task, that object influence via contact. So this is your first demonstration example. A human pretty quickly recognizes there appears to be a red thing and a blue thing, and then they appear to be together. And then in the next thing, you see, there appears to be a blue thing and the red thing. In the next thing, they appear to be together. And if you look here, it always appears to be the red thing going to the blue thing in the most direct way. So along the grid. That's all that the human needs to see. 2 examples, and most humans will already make that inference and can now solve. If there now is a test example where the blue thing is down here and the red thing is here, like this, and it asks you what comes next, you know that the red thing is going down to the blue thing. But it's very hard to train a machine to do this. So I like this test because it's sort of a different test. And I believe these tests weren't procedurally generated. These tests were actually generated by Chollet or by actual humans. That's pretty cool. And 1,000 tasks like this, it's going to be very hard to solve. There are even more abstract priors like goal directedness. So now here you can already see this a little bit in that you can say, well, the red thing wants to go to the blue thing. So there's a notion of time involved, maybe. There's also counting and numbers prior. So here you see like a time process. So in this demonstration example, you see blue things here, red big thing, and then the output grid is this green thing. And as a human, you immediately recognize, okay, so it shoots out from the blue thing, the green thing shoots from the blue thing, hits the red wall, and goes here. Now, try to make a machine understand this. This is insane, right? So if you look at the more examples, it appears that the blue thing always comes from somewhere like the side of the image, and the green thing comes out obviously from whatever is not at the border of the image, and then bounces off the red thing if it hits the red thing. Now here you can already see what's going to happen. Remember, your AI would need to first determine, okay, all of these output grids, they seem to be the same as the input grid. So it would need to explicitly construct the output grid in the same manner as the input grid because it understands this, right? This is not the same in every task. Then it needs to recognize the red thing, that it stays in every one. So it needs to put the red thing here, right, from here. And then it needs to recognize the blue thing stays as well. And then most shockingly, it needs to recognize, okay, I will draw a line in pixels, and lines in pixels are hard here. And then as soon as it would hit the red thing, it bounces off into the other direction. So from just these three examples, the machine has to understand that and correctly output the exact solution, not an approximate solution, the exact solution. Okay, so yeah, there are these basic geometry and topology priors like lines, rectangular shapes, symmetries, rotations, translations, shape upscaling, containing, being contained, drawing lines, connecting points, and so on. Now, let's look at some more examples. These are fun, right? Check out this one here. So you see green and red, and then somehow the green connected to the red, right? So this is an example of that has many of these priors in, many of these concepts in. There is goal directedness. You can already sort of form the hypothesis that the green wants to go to the red, but also you see that somehow it sort of appears to, the blue things seem to be maybe obstacles, and it appears to change direction when it encounters an obstacle, like here. So here you see the example, and you probably confirm. So your hypothesis could be it always goes until it hits, and then it changes direction towards the red thing, right? Always towards the red thing, because it's not always towards the right, because here it turned toward the left. So it goes somehow towards the red thing, and so it's pretty ambiguous in this situation, but you can also make the assumption that if it's ambiguous, it goes towards the middle, maybe. So here, again, now we're actually confirming probably. So we go towards the red thing, which would be towards this direction. Then we hit an object. Then we go towards the red thing until we hit an object. And then we go here. Also see that these grids here are not the same size. So it's not always the case that the grids within the same tasks are even the same size. So now here your AI would need to recognize what size of grid it needs to draw and what the result is. So it would need to copy this entire grid and also change these pixels right here to be green pixels. That's hard. I mean, I find this to be pretty hard. This is the line extrapolation and turning on obstacle and efficiently reaching a goal prior. That's crazy. And is there more? Yes, there is two more, I believe. Yeah, those are the last examples. So in this one, you can see right here, there appear to be objects, which there's these blue objects, they appear to be the same, and there are these red, and then the output grid is one of these blue objects. Okay, so here we again see different objects, the output grid is one of them. So as a human, you can already recognize the output grid is probably always going to be one of these objects, and now we need to decide on which one. So we can formulate the hypothesis that it's probably going to be the one that's the most. Like here there's 3 of the blue ones, here there's 4 of the yellow ones, that's more than any other. And this here confirms our hypothesis that it's the object that appears most often. Now, again, see that there's this notion of object-ness. You need to upscale somehow. No, this is not upscaled because the grid is the same size. It's simply the image that's upscaled. But you need to somehow be able to focus in on one of these objects. You need to count them. You need to compare the counts via each other. And now here you can pretty easily see that the output grid is going to contain one of those blue things as a human. And here it's sort of a symmetry filling task. Now, as a human, you need one demonstration to get this. Maybe you need more, but many tasks involve some sort of symmetry. Okay, drawing the symmetrized version around the version of a shape around a marker. That's going to be fairly hard for a machine to learn without the developer knowing that this task is coming. Okay. They highlight some differentiations to standard psychometric tests, but what I find interesting here is that this thing, what a solution to ARC may look like and what it would imply for AI applications. They say we have found ARC to be fully solvable by humans, so they've sat a human in front of every one of these tasks and it's solvable. While many ARC tasks are intellectually challenging, human test takers appear to be able to solve the majority of tasks on their first try without any practice or verbal explanations. In effect, in this task, you get 3 tries at each of the problems. You get three tries, and the humans can already solve it in 1. So that just shows you how cool humans are. So here is Chollet suggests a solution approach. Says start by developing a domain-specific language capable of expressing all possible solution programs for any ARC task. Since the exact set of ARC tasks is purposely not formally definable, this may be challenging. The space of tasks is defined as anything expressible in terms of ARC pairs that would only involve core knowledge. So core knowledge is this set of human priors that we discussed last time, like object-ness and symmetries and geometric shapes and navigation and so on. So he asks you to basically develop a DSL that can capture all the different tasks. So basically define a formalism of these tasks. But it's hard because you don't know what the tasks are going to be. So your best bet is probably to make a formalism that completely over-represents what the tasks can be, right? It would require hard coding the core knowledge priors from 3.1.2 in a sufficiently abstract and combinable program form to serve as a basis functions for a kind of human-like reasoning DSL. We believe that solving this specific subproblem is critical to general AI progress. Basically says whenever we can describe, this is like saying that AI progress will make a big step once we can formally describe human priors. And while true, I feel the hardness of this problem is as hard as actually building general artificial intelligence, or very close to it. So it is a bit of a like how to build AGI. Step 1, build AGI. That's sort of, I mean, not exactly, but it's kind of what this says, right? If I could actually have this DSL to describe every single task, and I could do it, such that it is not super over capturing all the tasks, then I would have described human core knowledge in a sufficiently accurate degree that I could just, build AGI. But he goes on, says, given a task, use the DSL to generate a set of candidate programs that turn the input grids into the corresponding output grids. This step would reuse and recombine subprograms that previously proved useful in other ARC tasks. So it says, whenever you have captured the core knowledge, or whenever you have captured the problem space in a formal language, you can simply use that formal language to express whatever your input is, that turn the input grids into the corresponding output grids. So you would put in these demonstration examples and describe this with your formal language that you have. And you can somehow reuse and recombine subprograms that previously proved useful. So basically asking you to come up with source code that would generate these demonstration examples in the language of your DSL. And then he says, select top candidates among these programs. So you would generate multiple versions of source code that generate these things based on a criterion such as a program simplicity or program likelihood. Note that we do not expect that merely selecting the simplest possible program that works on training pairs will generalize well to test pairs. And then use the top 3 candidates to generate output grids for the test examples. So I hope the approach here, I feel it makes sense, but it is sort of over hopeful in my mind, and that's mainly because of step 1. So step 1 asks you to come up with like a programming language that can capture all the tasks in this the data set, even though you don't know what the tasks are, and that has this human core knowledge inside of it in a formally describable way. And then once you have that programming language, you would, if you're given this task where you have a bunch of these demonstration things, and then you have the test thing, you would generate all the programs that would produce these demonstration examples, or that would, given the input grid, would produce the output grid, right? You would generate all the programs, and then you would select somehow among all these programs the one that you think generalizes the most, and you would use that program to put this in and get out the solution. And they say it's not always the simplest program, not always the shortest program, maybe, who knows? Like, I feel step 1 is the crucial issue here. Okay, so they say they make some claims here and about what this would bring the community. We posit that the existence of human-level ARC solver would represent the ability to program an AI from demonstrations alone, only requiring a handful of demonstrations to specify complex tasks. To do a wide range of human-relatable tasks of a kind that would normally require human-like fluid intelligence. As supporting evidence, we note that human performance on psychometric intelligence tests, which are similar to ARC, is predictive of success across all human cognitive tasks. Further, we posit that since an ARC solver and human intelligence would be both founded on the same knowledge priors, the scope of application of an ARC solver would be closer to that of human cognition, making such a solver both practically valuable and easy to interact with, and would produce behavior that is in line with human expectations. Okay, so they're making the same argument that anyone before has made, but they condition it on some things. And this is, I think, the conclusion of the entire article here of On the Measure of Intelligence, because people had this hope, and they say that here. Claims are highly speculative and may prove incorrect. Much like Newell's 1973 hopes that progress on chess playing would translate into meaningful progress on achieving a broad range of cognitive abilities, especially if ARC turns out to feature unforeseen vulnerabilities to unintelligent shortcuts. This is the AI effect, and it basically means that whenever you think a task, the solving of a task represents AI, and then you actually see the solution, then the solution turns out to be not AI in the eyes of the human. So the human, at first, they would say, oh, this task really requires intelligence. And then someone solves the task and they would say, oh, that's not intelligence. You kind of hacked your way to that. And the expectation is that in this ARC challenge, there might be a hacky way to that. But I mean, the good question is at what is there even a task like this ARC challenge here? Is there even a possibility of a task where you wouldn't say that? And I'm not so sure about this. They seem to be more hopeful than I am. But at least they say the ARC challenge is founded on the same priors as a human has. It gives you the same amount of experience as a human has, right? And therefore, it is much more comparable to human intelligence. All right, they go over some weaknesses right here of like criticizing their own thing. Generalization is not quantified, so they have a measure of generalization in the previous chapter, but they don't use it right here. Test validity is not established, dataset size and diversity may be limited, and so on. But in my mind, I would not consider this as like an AGI task or anything like this. I'm pretty sure the solution to this will come in a form, again, where people don't really think it exhibits intelligence. But I do like the task as such. And as a machine learner, I am very excited to think about how machine learning can go about solving this task. And especially with what we've seen from something like GPT-3, that has exactly this kind of structure where you train on a giant data set, blah, 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 you pre-train your language model, but then at inference time, you input a bunch of these demonstration examples and you ask it for the next output. So I feel that might be a good start for doing it. The question, of course, is what then do you pre-train this model on? This GPT-3 for ARC, what's the pre-training data set for it? And I guess that's going to be the challenge, and it's probably going to require people to specifically program all of these priors into a dataset generator for pre-training. So that would be my approach. My approach would be write a dataset generator for pre-training a GPT-3 model to do these kind of tasks. And in order to write the dataset generator, you'd have to basically program in all of these priors. And that's not going to be easy because your best bet is to sort of put yourself into the shoes of Chollet and be like, oh, if I were to design a task, what kind of things would I do? And then try to capture that. That's going to be your best bet. Your most honest bet with respect to the challenge is to try to, as faithfully as possible, implement something like an object-ness prior, where cohesion and persistence are captured. That would be the most scientifically sound approach to my approach. All right, so that was my take on the ARC dataset. If you have any comments, I'm very excited to hear comments on this. If you have already tried the ARC challenge, have some insight, I also welcome comments on that. And with that, I'll see you next time. Bye-bye.